Well, hi there. We're going to have a look at something extremely exciting in the area of specialist maths, and this is the whole area of parametric equations. And these are the most marvelous little devices you've ever seen. And so let's make a start. Okay, we're looking at parametric perfection, and we've got a circle there for you, and we've got an ellipse there for you, and we've got an hyperbola for you as well, just to give you a bit of a clue about these marvellous things. They're all part of the conics family, and that's what we're going to be dealing with. Yes, and we love them. They're beautiful things, and we can do them too. Well, you'll be able to do them after you've seen this video. That's what I hope, and I know, I'm confident that you will. Okay, let's go. Now, in this first part, this is going to be a two-part video because it's just too much to fit into one part. So part A is going to be the first video, Cartesian to parametric, and then part B is going to be going the other way from parametric to Cartesian. The subtitle I've given this is Scratching the Surface of the Cartesian to Discover a Whole New World, and boy do you ever. And the subtitle is Would the Real Independent Variable Please Stand Up? Because you thought that if you had a circle of x squared plus y squared equals 1, you thought x was the independent variable. Well, not true. Now, this is the Cartesian diagram. We've got I want you to imagine that is a, well, it is actually, it's a circle, a bit blurry, but it's x squared plus y squared equals 1. Now, that's what it is. Now, x is the independent variable. Yes, well, that's what you thought, but let's just have a good look at this. Often it isn't. Often it is not, okay? So, this is called the implicit form of writing the equation, when we don't make y the subject. So x squared plus y squared equals 1. That's the implicit form. The function form is the one I've just highlighted there. That is y. You solve it for y, and you say y is plus or minus the square root of 1 minus x squared in that case. So that's function form. So far so good. X is the independent variable. Yes, well, kind of. It's not always. It is when you're just dealing with Cartesian, yes. But when you get into parametric, it's not anymore. So y is the dependent variable in that case. Yes, it is. And now, as you see, I've solved that into function form. Y was plus or minus square root of 1 minus x squared. So the plus bit is the upper half, the semicircle above the x-axis, and the minus bit is the lower half below the x-axis. In case you never quite got that bit before, there it is for you. Now, I'm saying that the domain of x is from minus 1 to 1, square brackets, so that's including both minus 1 and 1. And what else have I said here? Yeah, is that the end of the story? Well, you may ask. No, it's not the end of the story. It is not. Look at this. Ha-ha, there's hidden truths beneath the surface, and the circle is going to tell us something. What have you got to say to us, Mr. Circle? Ah, well, we can hardly wait. Thank you for the tip-off. So, let's go and see what we can discover. Oh, this looks suspiciously familiar. This looks like our unit circle from circular functions. Only we're going to look at the parametric significance of this. Okay, so we do have the unit circle. We're revisiting, we're having a reunion with the unit circle, as if we need that, from circular functions. So, now you remember, in this particular case, that is a circle of x squared plus y squared equals 1. That's the x, and that's the y, oh yes, and there are coordinate points of that point A on the, you can hardly see that little a, but it's that point on the circumference, yeah? And we're imagining that there's a pivot or a hinge at the centre of the circle at point B, and that little point A on the circumference is free to move around. Move around from the 3 o'clock position, highlighted in blue there, the x-axis. That's considered to be 0 degrees. Now, look what's happening here. We're actually considering the angle and what the effect of that angle is on x and y, aren't we? Yeah, in fact, x equals cos theta and y equals sine theta. Now, do you see what's happening here? X and y are now, in terms of our paradigm that we're considering here, our model, they both depend on theta. Do you get that? Theta is now the independent variable, not Mr. X. Ha ha! We're now entering the world of parametric perfection. In fact, so x is a function of theta, y is a function of theta, and we could now replace the coordinates that we had for that point A, which was x and y. We're now replacing it with cos theta and sine theta, because the whole thing is driven by theta. Theta is the third variable or on which x and y depend, and therefore theta is called the parameter. Da-da-da-da. And x is cos theta, y is sine theta. This is parametric form, parametric equations. Do you see what I'm going on about now? Why I'm getting so excited? Well, you probably don't, because I get very excited anyway. But maths is exciting. It's just the most amazing, wonderful thing. So they are parametric equations, folks. You've got it now. See, so underneath the surface, scratch the surface of x squared plus y squared equals 1, and you might get a whole new world of wonder under there, driven by theta. So theta is the engine driving x and y. Wow, what have we got now? But wait, there's more. Oh, there couldn't be more. Heavens, we'll pass out if there's any more excitement. Let's animate our unit circle radius. Oh, wow. Anti-clockwise. Oh my goodness. So we're going to say theta now depends on t. In fact, it's directly proportional to t, where t is the time in seconds. So we're just going to motor our little theta around that circle like a radar screen thing, if you know what I mean. If you've ever seen radar, just zooming around the circle all the time. So we're going to say x is cos theta, which in fact will be cos k times t, where k is a constant. T is going to be greater than or equal to 0 because you can't have negative time. T will be time. And y is sine theta, which is sine kt for the same conditions. Now, I'm just trying to make it a bit more interesting by saying in the next line, let's say we make one revolution take, say, 8 seconds, which would be 2 seconds per quadrant. So t, which capital T is the period, which equals 8, which equals 2k. The period is 2k over the number in front of the t after the sine or cos sign. So 8 equals 2 pi over k, and therefore what's k? Yeah, k equals pi over 4. So therefore we can say that x is cos of pi t over 4, y is sine of pi t over 4. So our independent variable now is t. That's right, and that's parametric form. Do you like that? It's pretty amazing. So let's just show you what's going to happen to our... I've done a fairly crude animation in the screens to follow, but I want to just show you. That's parametric equations. Here we go. There it comes. Ready, set, go. There, I animated around the screen for you. Isn't that exciting? So now let's see what else have I got for you. We're back to our unit circle. Okay, now, what is the difference between parametric form, x equals cos of pi t over 4, y equals sine pi t over 4, and the function or implicit form? Well, look, in a nutshell, I've gone to a lot of trouble on this screen to try and explain it all, but look, the summary is that for parametric form, you get real-time information. You get the snail trail happening as you look at it in real time as to what x and y are doing in the various stages from t equals 0 onwards. You see the trajectory. Whereas if you just look at function form, all you see is a snail trail. You just see where they've been. You've got no idea where they were at what time. So that's it in a nutshell. But here we go, explaining it all in excruciating detail. There's theta, okay? Theta equals pi t over 4, in our case, for an 8-second period. And t is greater than or equal to 0, yep? Now, so therefore, there's our coordinates. X is cos of pi t over 4 and sine, y is sine of pi t over 4. And Yeah, the motion starts there when t is naught, because then if you think about that, x is cos of naught. If t is naught, that is 1, cos of naught is 1, and y would be sine of naught, and sine of naught is naught. So it'll start off at 1 and naught. That's when t is naught. And that's it. Okay, that's what I just said. Okay, now, the other exciting thing is we can now work on, we've got its starting position. In other words, we've got real-time information here, which you never get for just Cartesian. And we're going to work out the direction of the motion. Oh, shock horror. We really are going to work out the trajectory of this thing. So for the direction of motion, you test the position when it's done a quarter of a cycle, okay, from its starting point. So a quarter of a cycle, when theta is pi on 2, that is, for an 8-second period, t would be 2 seconds, yeah? So, there we go. Now, cos of pi on 2 is naught, right? That's the x bit. And sine of pi on 2 is 1. That's the y bit. So, in other words, in a quarter of a cycle, this little beastie will be at coordinates 0 and 1. That is, what I've said there is we're testing the position after a quarter of a cycle, plugging in those values into the x formula and the y formula in terms of t. And there is its position after a quarter of a cycle. So can you see which direction of rotation it is? Well, of course you can. It started off at the 3 o'clock position, if you like, using Air Force terminology, and it's finished off at the 12 o'clock position after a quarter of a cycle. It is going anti-clockwise. Yay! There you go. Isn't this marvellous stuff? I get so excited talking about this. It's great. I love parametric equations. They're just such fun. Now, what else did I have here for you now? Ah, yes. So now I'm sort of saying, and I'm revealing it all to you, with parametric form we get real-time information on the position and direction of movement. Yes, we do. But with x squared plus y squared equals 1, you lose all this and you just get the snail trail of where it's been. No real-time info. You see? That's it. Oh, goodness, I got another question. So what is this question? With parametric, or which parametric population of equations below the surface in the new world of theta driving the x squared plus y squared equals 1 equation, which parametric population of equations could produce this Cartesian graph? Well, I think we just had one before, didn't we? We said x was cos of theta, and we said y was sine of theta. Well, that surely is the one, isn't it? Well, sometimes the truth is stranger than fiction, because the answer is the list is endless. Oh my goodness, how can that be? Yes, I agree with that. Well, we're going to reveal all that in the next screen, but firstly we're going to go through a few rules here so that we don't get completely carried away with ourselves and lose the plot. Now, okay, here comes a few ground rules for these circles and how they morph into ellipses and other things, and some other stuff thrown in. Right, for circular motion and for elliptical motion, one of the x function of t and y function of t parametric equations must be in terms of sine of kt, and the other one must be cos, okay? One has to be sine, the other one has to be cos. If you've got that, the x is either sine or cos, and then the y is the other one, if you know what I mean. That'll get you a circle or an ellipse, okay? That's the first thing. Now, second thing is, depending on which of the x or the y is sine, and which is cos, and on the SIGN sign of the coefficients of those sine and cos terms, that information determines both the starting point and the direction of motion. And I'm going to reveal all that direction of motion stuff and starting point in the next screen. It's a mind boggler. So But that's what I'm saying, okay? So go over point 1 again. For circular motion and elliptical motion, one of x and y has to be sine and the other one has to be cos, right? Point 2, depending on which is sine and which is cos and which is plus and which is minus, or whether they're both minus or whether they're both plus, it doesn't matter, but that determines both the starting point and the direction of motion, yeah? Right, the third one is for circular motion, the numerical coefficients of sine and cos must be the same. Okay, they must be the same. So if you're going to have x is 2 sine t, then y would have to be a 2 in front of the cos t, if that's the way it goes. You know, like you'd have to have the same coefficient, right? That's for circular. If they're not the same, you've got yourself an ellipse, a squashed circle, okay? So if you had x as 2 sine t and y was 3 cos t, that is an ellipse, okay? But on the other hand, if you had x was 4 sine t and y was 4 cos t, that is a circle, okay? Now I've squashed one little more point down there where there's no room. Watch. Woo! To speed up or slow, now this is the most exciting bit of all, to speed up or slow down the motion, all you have to do is change k, okay? The higher the k number, now you work that out. If the period is 2 pi over k, the higher k is, that means the slower the period's going to be. Isn't that right? 2 pi over something bigger makes it something smaller for the period, doesn't it? Yeah, the period. And therefore the frequency is higher. If the period is lower, therefore the frequency is higher. That's how it works, okay? Oh, this is so exciting. Now, come on, we're going to do the next screen now. And you're going to have your socks blown off. Here we go. Now, have I got it? Yeah. Okay, so the original question was, about 2 screens ago, which parametric functions give rise to this x squared plus y squared equals 1 thing? Now, just be patient with me while I show you some of this stuff, because it takes a little bit of assimilating. Okay, the one that we already did was x equals cos of kt, whatever k is, and y equals sine of kt. That's right, isn't it? Yeah? Now, we're going to try and analyse the starting position and the direction of motion. So just go with me for a minute. Oh, my goodness, I'm getting puffed out. Now, because there's so much to cover, see? Now, when t is naught, this is where you're analysing the starting position. When t is naught, x is 1. If x is cos t and y is sine t, you'll get 1 and 0 for the starting position. Right, so let's just put that in. Da-da-da-da, there it is. Now the direction of x motion. Now this is a little bit hard to follow, so just go with me here. Now the x motion is, x is cos of kt. Now I'm going to draw a little graph up here of x is cos kt, okay? Now you've got the x is written in the vertical plane there, the per vertical axis, and the t is written in the horizontal, if you know what I mean, because this is a parametric equation, okay? So don't be confused where the x is sitting where the y usually does. This is x versus t, or kt actually. Now, what we have to do here, folks, is we have to work out what the x motion is doing in real time, but without the assistance of the measurement of t along that horizontal axis. We just have to look at the x motion, the cos motion. So imagine yourself, that's a roller coaster, and you're starting up at x is plus 1, and you're going zooming along that graph from the x highest position down to the x lowest position and back up to the x highest position. That's what the cos graph is doing, okay? Now, if we stripped away that time axis and just looked at the x bobbing along its own axis without measuring specifically where it is at each time by virtue of the time axis, let's see what we would get. We will remove the t-axis, okay, and we'll just see what x does on its own axis, because that's what we have to translate this into, both the x and the y motion without the t in the big picture, in the Cartesian picture, okay? Right, now let's show you, let's just have a look at it. I've tried to draw the x motion on that little graph there starting at its top point and going down and back up again without the T business happening, or at least moving along the T axis. Do you see what I did? Okay, do you want to see it again? Here it comes, right? Look. And back up again. That's the cos graph, the roller coaster without moving horizontally to show what's going on each x at a specific time. Now I'm going to put that onto the big circular graph, starting at 1 and 0 and moving from its maximum. There it is, moving from its maximum, go down through the origin to its minimum point and moving back to the maximum value of x. That's the x motion translated onto the x Cartesian axis of the big circle. Do you get that? Yeah, it's once you see it like that, it's kind of easy to sort of get, but you know, it can take a while, so don't worry, you might have to look at it again. I'm rubbing all that out again because we're going to do y now, but now the direction of x motion, the initial direction is that away to the left from that point where 1 and 0, right? Yeah, from there. So where is it? It's going that away, yeah? Moving towards the origin. Do you see that? Okay, good. Now we're going to do the y bit now. We'll do it all over again for y now. Okay, the direction of y motion is sine. It's sine. Okay, it's not cos, it's sine. So let's just draw the graph of sine kt now for y. Yeah, it's a sine graph. So if you were on the roller coaster there, you'd be going from the origin to the up, to the maximum. Then you'd be going down the Big Dipper to the -1 position. Then you'd be going back to the origin again. And if you didn't have the luxury of that horizontal axis to show you where y is at any specific time, and just looked at the y bobbing around on its own axis without the horizontal time axis, what would you see? What would you see? My goodness, it fills me with glee. Oh, sorry, I'm a poet, I can't help it. Now, what is all that? I think I'm just trying to say, yeah, the y is going to move like this without the time thing. You ready? You ready? Here it comes. I'll just do it again for you. It starts at the origin in case you missed it. Origin up to the max, down to the min, and back to the origin. Now we're going to translate that onto the big Cartesian graph from the origin going, there it comes. Now you ready? Up we go to the maximum, down we go to the origin, down we go to the minimum, and back to the origin again. Okay, that's what you do. But the thing is that we're starting our journey at 1 and 0. X is 1, y is 0. So let's just translate that initial motion of y at time t is 0. Starting from that point 1 and 0, it's going to be obviously travelling upwards towards the max from the origin, isn't it? There it is, right? Going up, 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 up. Now look at the x and look at the y. The x is trying to pull us in towards the origin. The y is trying to pull us up, away from the origin. So what is the combined motion? What is the combined vector addition of those motions? Yeah? You can see it now. You see? Look, you can see how it's going anti-clockwise, can't you? Of course you can. It's going to go anti-clockwise from that position, that starting position. Oh, that took a lot of explaining, but I think you'll get it now, won't you? Right. Now, that was the first one that we did originally. Now, there's actually 8 functions that can all start in different positions and all go different ways. Variants of that particular one there where I've got x as cos of kt and y as sine of kt. Have a look at this. We're going to start. That's the first one, right? Here comes the second one. Oh yes, in the same way, I've written this for you. In the same way, I want you to prove the following. These, I'm not going to prove them all. It takes too long. But you've got the basis for it now. Prove it for yourself. Okay, here comes the first one. Or the second one, actually. If x is cos of kt and y is now minus sine of kt, what that will do is that will start at the same point as we've just got before, but its direction of motion will go the other way. It goes clockwise. Oh, wow. So there's that one. Now, here comes another one. This time we've got x is minus cos of kt and y is plus sine of kt. So that's going to start over, where does that going to start? That starts at minus 1 and 0 if you test it out when t is 0. And the direction of motion for that one is that way. So that's, what's that? That's clockwise, isn't it? Gee, willikers. So there's the third one. Here comes the fourth one. If x is minus kt and y is minus, minus cos of kt and y is minus sine of kt. Now the starting point for that one is minus 1 and 0 like the previous one, but the direction of rotation is this time is anti-clockwise. Okay, now there's four more, and we get those by reversing the x to a sine term and the y to a cos term this time. So if x is sine kt, y is plus cos kt, that one starts at 1 and 0, that's right up the top, and the direction of rotation is that away, which is, I'm getting confused now, that's clockwise, isn't it? Okay, next one. If x is minus sine and y is plus cos, that starts at the same spot there, up at the 0 and 1, and that goes the other way. Okay, two more, as if you weren't confused enough. X is now sine and y is minus cos, and the starting point is 1, 0 and minus 1, and which way does that one go? That away. Prove all this to yourself. Look, you'll have fun doing it, and boy will you understand it better if you do. And the last one is x is minus sine and y is minus cos, and that's going to go, starting at the same spot there, 0 and minus 1, and it's going to go that away. Ah, my goodness. So now, here comes the final knockout punch. Check this out. Okay, now, I said that there were infinitely many solutions, didn't I? Okay, well I've only given you 8 for x squared plus y squared equals 1. Okay, to obtain the infinitely many parametric equations for x squared plus y squared equals 1, you speed it up or slow it down. And how do you do that? By simply changing k. Wow, isn't that something? To any value you like, okay? That is so marvellous. So, alright, so now, my goodness, there's a lot of stuff I covered there. Now, oh look, the circle is morphing into another smiley face. Just tell you how excited he is. This is parametric perfection. Truly, truly parametric perfection. Alright, Mr. Smiley Circle, we get the message. We're pretty excited. What else? Have you got anything else to say to us? Oh, good heavens, how can this be? More excitement? More excitement? How can that be possible on the next screen? Oh, I don't think I can cope with this. I won't be able to get to sleep tonight. Anyway, alright, we'll try. What are you saying? Question. Alright then, what's your question? What happens if the k in sine of kt is different from that in cos of kt? Well, hang on, what are you talking about? I thought they had to be the same. You mean to say they can be different? Oh. Well, we know if they're the same. Hang on a minute, this is doing my head in. Okay, if x was cos of t and y was sine of 2t, that's not necessarily a circle at all, is it? Because if x is cos t and it takes a certain amount of time to do one period, and sine is 2t, which means it's going twice as fast, that means in the time that cos takes to do a half of its thing, sine's already done all of its. So that means sine would be doing 2 periods when cos would be doing 1. I think. Think about it, yeah. Pause the video until you have an answer. The answer is on the next screen. Oh, wow. Well, what about if x was cos t and y was sine 3t, not 2t? Oh, my goodness. Heavens above. Well, we'll have to think about that. The answer is on the following screen. Alright, okay, alright. What else? And what is the starting point for each of these? How would you change the starting point? Alright, now, did you get all that? There's a lot of learning for you in this particular screen. A lot of learning. think about it, and if you connect the dots, my goodness, you own it. Okay. Now I'm going to give you the answer. I hope you've paused the thing and had a go at it first. All right. Play, have fun. Yeah, play, have fun. All right. I will reveal the next screen to you. This will be x is cos t and y is sin 2t. Oh wow! Look, it's a toy train track. Look, it's a toy train track. Now you see if you can figure out how we got that. What's the starting position? It's there. What's the direction of motion? It's there. Yeah? Okay. And what about this? What about if x was minus cos t and y was minus sin 2t? What would happen then? That would be your starting point. You prove that to yourself. And what about the direction of my rotation? You figure it out. It's going to be that way. Okay? Alright, now here comes, play. Play with other things. What about if you reversed them? Made x sine instead of cos and y cos instead of sine. What would that do to the shape? Pause the video and have a look at it and see what you get, you know? And, this is where x was cos t and y was sine 3t. Well, if you live in Australia, you've got the ABC news symbol. There you are. And if you're in America, you don't know what we're talking about. But that's that one. Isn't this great stuff? There's the starting point. There's the direction of rotation. There it is. And what about if we... I don't think we can cope with any more. Change things around. We've finished part A, Cartesian to parametric, and in part B, we're going to do parametric to Cartesian. So that was a very, very action-packed video, wasn't it? Alright, well I'll see you in part B. Hope you enjoyed it.